Carnot cycle, learn about the second law of thermodynamics, analyze amount of heat absorbed and net work done during Carnot cycle, find out the efficiency of Carnot engine. French engineer Nicolas Leonard Sadi Carnot in 1824 led to the discovery of heat engine called Carnot engine. He also showed that this engine is the most efficient engine which operates in an ideal reversible cycle called as Carnot cycle. The Carnot engine establishes the maximum limit on the efficiency of all other engines. In other words, the system working through the Carnot cycle produces the maximum amount of work from given amount of energy supplied to the system. Now, we shall discuss Carnot cycle in detail. Before learning about the Carnot cycle, the concept of reversible and irreversible process should be discussed. A reversible process is the process by which system can be brought to its initial state along the same path, and for which every point along the path is an equilibrium state. In reversible process, the dissipative effects which convert mechanical energy into internal energy are not present. An irreversible process is the process which violates the above requirement. The most natural processes are found to be irreversible in nature. The heat engines are the device which are cyclic in nature, and its working fluid returns to its initial state at the end of each cycle, and hence work is done by the working fluid during each part of the cycle. In one part of the cycle, work is done on the working fluid, while in other part of the cycle, work is done by the working fluid. The difference between these two work is the net work done by the heat engine. The efficiency of heat engine cycle depends on the execution of individual processes involved in the formation of the cycle. If reversible processes are used, then the efficiency or net work produced by the system can be maximized. The best reversible cycle known is Carnot cycle. Carnot used a reversible cycle to derive the maximum convertibility of heat into work. Carnot cycle consists of a system of 1 mole of ideal gas that is subjected to series of 4 reversible processes, commonly termed as 4 strokes. These are given below. Stroke 1 is the reversible isothermal expansion. Let us suppose that the temperature of the gas at initial stage be T2. Now the gas is allowed to expand isothermally so that the volume changes from V1 represented by point A to V2 represented by point B in figure. As the expansion of the gas takes place, the temperature of the gas starts decreasing. But as soon as the temperature drops by an infinitesimal amount, the gas absorbs heat from the reservoir. And let Q2 be the amount of heat absorbed at temperature T2, and thus raising the temperature back to T2. Since in the isothermal expansion of an ideal gas, the temperature of the system does not change, therefore delta U is equal to 0. From the first law of thermodynamics, that is delta U is equal to Q plus W, we get Q equals to minus W, that is the heat absorbed by the system is equal to the work done by the system on the surroundings. The total heat transferred to the gas during this process is given by equation 1, that is Q2 is equal to minus W1 is equal to R T2 ln V2 by V1. Stroke 2 is the reversible adiabatic expansion. At state 2, the gas is allowed to expand reversibly and adiabatically, and the volume changes from V2 to V3, that is from point B to C. During the expansion, the work is done by the system. As the system is under adiabatic conditions, therefore no absorption of heat can take place. Therefore, the temperature of the system falls from T2 to T1, let us suppose. Since Q is equal to 0, therefore, according to the first law of thermodynamics, we get delta U is equal to W. As the work is done by the system, therefore, conventionally W is taken to be negative. So, delta U is equal to minus W. Since Cv is equal to du by dt at constant volume, we can write delta U is equal to Cv delta T, which is equal to Cv T1 minus T2 equal to minus W. Change in temperature delta T is equal to final temperature minus initial temperature, or minus W is equal to minus Cv into T2 minus T1. Let the work done by the system at this stage be denoted by W2. Then we have equation as minus W2 is equal to minus Cv into T2 minus T1. Stroke 3 is the reversible isothermal compression. At state 3, the gas is allowed to compress while keeping the temperature of the system constant. As the gas compresses, the volume decreases from V3 to V4 depicted by point C to D in the figure. During compression, the temperature tends to increase. But as the temperature starts rising, heat flows from the system to the surroundings. Thus, the temperature decreases, making the overall temperature of the system constant. Since the compression is done under isothermal conditions, therefore, delta U is equal to 0. Let Q1 be the amount of heat released to the surroundings, which is negative as the heat is released at temperature T1, and W1 be the amount of work done on the surroundings during the compression. Conventionally, it is positive, and these are given by equations as minus Q1 is equal to W3 is equal to RT1 ln V4 by V3. Stroke 4 is the reversible adiabatic compression. At state 4, finally, the gas is compressed under adiabatic conditions, and hence the gas returns to its initial state, state 1, having the volume V1 and the temperature T2, represented by point D to A in the figure. During compression, the work is done on the system, and hence it's positive according to the sign convention. Applying the first law of thermodynamics, that is delta U is equal to Q plus W, work done will be equal to delta U as Q is equal to 0 in the adiabatic conditions, thus giving us equation as delta U is equal to W is equal to Cv delta T, which can be further written as Cv into T2 minus T1. Let W4 be the work done at this stage, and it is given by equation as W4 is equal to Cv into T2 minus T1. Here, T2 minus T1 is the rise in temperature produced by the adiabatic compression. The net heat absorbed Q by the ideal gas in the whole cycle is given by equation 9 as Q is equal to Q2 plus minus Q1, which can be further written as RT2 ln V2 by V1 plus RT1 ln V4 by V3. Or this can be written in the form of equation 10 as Q is equal to RT2 ln V2 by V1 minus RT1 ln V3 by V4. For adiabatic expansion, the equation can be written as, for stage 2, we have equation in the form of Cv ln T2 by T1 is equal to R ln